Hey everyone, today we're going to do application problems with hyperbolas. Before we actually get into the problems, I want to talk about a couple of things regarding hyperbolas. First of all, by definition, we talked about this briefly when we first introduced hyperbolas a couple days ago. We said that a hyperbola is a set of points in a plane, the difference of whose distances from two fixed points, called foci, is constant. That's by definition what a hyperbola is, but graphically, let's kind of figure out what that actually means. If I have a hyperbola drawn in, I have it here, and roughly right about there. So there's my hyperbola. Oops. Okay, so there's my hyperbola. If I were to pick a point, so let's say I were to pick this point right here, I'll call that point P, right there on my hyperbola. That point P, remember here's my center. My center's at 0, 0. My foci are located right here, so the coordinates of this would be C, 0, and this would be negative C, 0. We'll call this F1 here, foci 1 and foci 2. Okay, what this definition is saying is that I can take the distance from that foci, to this foci. If I call this D2, then I call this D1. It doesn't really matter which one you call which. But if I take the difference of those, and I'm going to take the absolute value because it just depends on the order that you do it. And remember, distance is always positive. That distance is always going to be 2a. Okay? It must be constant, and it's always going to be 2a. That's what, by definition, what a hyperbola is. And so we're going to use that concept when we're doing these application problems. So here's the kind of the takeaway from this. You want to use the foci, use your foci in the application problems. So if you want to make yourself a little note. These problems are pretty different from the other application problems we did, but I want you to be aware of this. Okay, because you're definitely going to use this concept as we go through these. So let me show you what I mean. Let's look at this example. And it says here that an explosion is recorded by two microphones that are 2 miles apart. Okay, microphone 1, they call that M1, received the sound 4 seconds before microphone 2, which is M2. Assuming sound travels at a rate of 1,100 feet per second, determine all the possible locations of the explosion relative to the location of the microphones. Now, if I just looked at that, I would probably be overwhelmed and not really sure where to start. But let's start by drawing ourselves a picture, okay? Our microphones are 2 miles apart. If we place our microphones at our foci, like we said here, up here, use the foci in the problem. If we place our microphones at the foci, that's really going to help us set up the problem. So, if I set it up, let's do this. So let's do this in blue. So here's one branch of my hyperbola. Here's the other branch of my hyperbola. Here's my foci here and here. Okay, so I'll call this microphone 1 and I'll call this microphone 2. Okay, my explosion is happening somewhere here. That's where my explosion is. Okay, and it says here that it microphone 1 received the sound 4 seconds before microphone 2, which is why I placed microphone 1 on the right and microphone 2 on the left. You could have done it the other way around, and I'm not really sure why I gravitate towards doing things on the right-hand side. I just do. You could have put the explosion over here on the left and then just had M1 on the left. Doesn't really matter. You're still going to come up with the same answer. Okay, my microphones are 2 miles apart, which means that the distance from the center to each microphone is 1 mile, right? So if you think of this, right, this distance here is 1 mile, and then this distance from that microphone to your center is also 1 mile. But I've got this information here about sound traveling 1,100 feet per second, so I'm going to convert my miles into feet. There's 5,280 feet in a mile. Okay, so 280 feet there as well. Okay, and the only reason I converted it into feet is because of this other, the speed units that we have is in feet per second. They don't give it to us in miles per second. Okay. Okay, now we need to figure out the value of 2a because that's going to help us figure out these distances. Okay, so we need to figure out the value of 2a. That's kind of where we're going to start here. And let me be clear, when it says determine all the possible locations, they're not asking you for like the actual, like you're 10 feet from microphone 1 and 500 feet from microphone 2. They don't mean that. When they ask you to determine all possible locations, they're actually looking for the equation. They're asking you for the equation of this hyperbola. Okay? So I just want to be really clear that that's what they're looking for. So remember, in order to find the equation of a hyperbola, we need that a squared and that b squared. This is a hyperbola centered at the origin. So remember the form that we're looking for, x squared over a squared minus y squared over b squared is equal to 1. So I'm looking for a and I'm looking for b. Okay, those are the two things that I'm looking for. So let's start out with some information from the actual problem. Okay, it says here that microphone 1 received the sound 4 seconds before microphone 2. So if I take 4 seconds and I multiply that by 1,100 feet per second, right, because that's how fast the sound travels, that must mean that microphone 1 and microphone 2, right, are 4,400 feet apart. Does that make sense? If you think of it this way, think of it as it's 4,400 feet farther away. The explosion is 4,400 feet farther away from microphone 2 than from microphone 1. Okay, so think of this. We know then that 2a is going to be 4,400 feet because 2a is the differences in these distances. It's d2 minus d1. Okay, so I'm saying that that difference between those is 4,400 feet because of the fact that microphone 1 received the sound 4 seconds before microphone 2. Okay, so 2a is 4,400, which means that a is equal to 2,200 feet. Forgot to put feet in there. Now, the other piece I need, so I know what a is, so I know what a squared is, but I don't know what b is. However, I do know c because remember c is this distance here. And I know what that is. I know that's 5,280 feet. So, I can go ahead and do c squared is equal to a squared plus b squared. That's our formula when we're doing finding equation of hyperbolas. So we've got 5,280 squared is equal to 2,200 squared plus b squared. And when you do that all out, you end up with b squared is equal to 23,038,400. Okay? So our equation comes out to be x squared over a squared. So if I square 2200, I end up with 4,840,000. So 4,840,23 minus y squared over 23,038,400 is equal to 1. And that's the equation for this particular hyperbola. So that describes all of the possible locations of where the explosion can be. Okay, so a couple of things to note. Let me just go back, and I am going to actually do the other two example problems that are on your note sheet in another video, just because I'm going to run out of time in this one, okay? But a couple of things. Remember that by definition of a hyperbola, the difference from a point on your hyperbola, if you measure the distance, the difference of the distances from a point anywhere on your hyperbola from one foci to another, that is always going to equal 2a. Okay, that's always going to equal 2a. That's by definition what a hyperbola is. So we're going to use that to our advantage when we're doing these problems. Okay, so again, it says here that the microphone 1 received the sound 4 seconds before microphone 2. Okay, because it received it 4 seconds before and sound travels at 1100 feet per second, I know that that explosion is 4,400 feet farther away from M2 than M1. And so by definition, that is 2A. Okay, and then we can find A and subsequently find B and get our equation. Okay, I'm going to stop the video here. I'm going to go ahead and put the other two example problems in another video. Thanks, guys.